Good afternoon to everyone. The student lecture will be given by Prognadipto Majumdar. He is a second year student doing M-Math at ISI Kolkata. His topics of interest are quantum and low dimensional topology, algebraic topology, and representation theorem. I welcome him to speak on twist, entangle, and tie the knot, a glimpse into Khovanov's magic. Please post any doubts you have in the meeting chat or ask him during his presentation. They will be addressed at the end of the presentation in case anything is missed. Over to you, Prognadipto.
Thanks. It feels great to come back to my college after so long, even if online. So, to all the participants, I would say, I prefer if you ask me. Whenever you're stuck or when you want to say something, just unmute and ask. So, that's fine. It's a great honor. So, let's begin. So, first of all, I'll today talk about why I'm interested in knots and what's there to study and all the stuff. So first, let's begin with a little bit of history. So historically, you can see that we have this Srivatsa knot. It has deep cultural significance. It's actually some figure of some endless knot. It represents something. Just look it up. So, and here this is the different kinds of knots which we see in real life. These guys. So we call them knots, but for instance, look at this guy. This is not really a knot. Why? We'll come back to that. And here you can see some knotty structure of some protein biologists use, and when they transform one protein to another, sometimes these knot things come into play. And by the way, this is very important to biologists. This stuff I won't be able to talk about because it's one of the things I don't understand. I do the math. So enough of history. Now let's go to the topic. So how did it all begin? The funny thing is that the study of knot theory first began by studying a wrong theory. So why it's wrong? So at the time, this guy, he was into physics and maths. There was some theory of ether and stuff like that. So they used to say that all the molecules, they look like some knots of some strings entangled in some way, and each of them represents a molecule. So what he wanted was to build some kind of periodic table. And that's why he tried to compute these knots. So we don't care that it was physically a wrong theory. This was one of the most important things in the history of knot theory and topology. And later on, this guy got interested and gave some nice conjectures about knots known as states conjectures. Sorry. Yeah. So over here, you can see this 10-fold knottiness. He's trying to draw all possible pictures of knots with 10 crossings. Now, the main question is that, so from this figure, how can you say that these are all the same and these are all not same? That's the first question. How can you say that this knot is not the same as this one? And the point number two is that, how do you say these are all possible knots of 10 crossings? That one he tried to prove. But later on, people found out that it was a lot of redundancies in this picture. He drew a lot more than there actually is. Now, that brings back to the question, when do we say that this is the same knot? Okay. And yeah, first, now let's define some stuff. So we're trying to do some nice embedding of a closed circle. So this requires an explanation. So this is a closed circle, and whenever I talk about S1, this is it. So you are allowed to twist it, you are allowed to pull it, stretch it, and whatever is like some elastic rubber band, you can stretch as much as you can. This is the same thing as this guy, but inside 3 dimensions. So how, now you say, how does the trefoil become the S1? How do you transform this to this? So under nice embeddings, why is this equal? That's the first question. So you have some knot, you tie the knot. How do you tie the knot? This part you choose one part, your favorite part. Okay, I don't know what's happening. Okay, so this part you expand and the other parts become smaller and smaller. So this part becomes smaller and smaller, and you take a rope, the way you tie knots in day-to-day life, the same way you do that. So that gives a continuous map. So let me write it down. Tying a knot is a continuous map. But it's not a nice map. So I have not defined what is nice. And I'm not going to define that. The thing is that you can't exactly stretch it to inside the string. So there will be some knotted point here, right? If you tie the knot, this is a knotted point. That point we call the point of singularity. So that is not a nice point. That's where the word nice comes in. So when you want to do more math and you have advanced stuff, you call it smooth instead of nice. And then I have to define what is smooth. So I don't want to go into that. So leave it. There won't be any knotted points here. That's what I want. So, and going by the knots, so you can talk about the connected components. So this is one component. A connected path component means that you can travel from one point to the other. And over here, you can see that the parts of the same color, you take any point here and you take any other point here, then you can travel from one point to the other. So that's the blue part is connected and the yellow part is connected, and they're not connected to each other. So it has 5 connected components. So I can say there are 5 circles in this picture. So it's a link. That's why it's a disjoint union. And tangles means that along with the circle, I can bring in some open strings. This is a tangle. This is a tangle diagram. Yeah, let me draw it some even more wildly. Yeah, this is a tangle diagram. And I can also include some circles. Yeah, you can do that. So why do we do this? So the basic question is that, okay, before the basic question, let's look at some interesting examples. So these are just examples. Just have a look, have some fun. That's how many different kinds of knots look like. And these torus knots, these are one of the most important kinds of knots in theory. So this 3,2, this means that this loops around the smaller circle 3 times and along the bigger circle twice when you project it onto one of these. So that's the notation. And a torus is, this is a smaller circle and this is a bigger circle. So far, so good. And so far, if you have any questions, just feel free. And the biggest question is, how do you say that 2 knots are same or different? The problem which Tate faced, and he did not face maybe himself, but there are a lot of diagrams representing the same knot. Now our question is, so when do we call 2 knots as same or different? And just have a look. So this is a very nice looking circle up to stretching. And this is also the same circle up to a bad kind of stretching. And just how bad kind of stretching do you need to transform this into this kind of figure? I know that this is the same, but how do I prove it? And what do I exactly mean by 2 knots being the same? So I have some knots in my hand. So I can twist it and turn it in 3 dimensions. So that's fun. I can do it in 3. So here's a knot. I just tie it inside. So I have not done anything else. So this is also another knot. And this is not a point. I have not shrunk it down to 1 point. It has some volume. So I can say that this is some valid knot. So these 2 knots are the same. So I can twist and wiggle in 3 dimensions. That's all I have. Now,
Brother, can you please repeat this part? That point, you have not shrunken that to a point, and
yeah, sure. So can you see this?
yes.
You can see this. Okay.
Yes.
So now you have, now look at this. I'm tying a knot. Okay.
Yes.
I'm making it tighter.
Fine.
And here we have this kind of diagram. So in real life, I know that the string thickness cannot be 0. This is not exactly a point. So
Yes, yes, obviously. Yes.
this is okay. But mathematically, now replace this by one-dimensional perfect line. Okay.
Yes.
Suppose this is a line.
Yes.
So I am doing this. This is the, I'm doing this, and just imagine that this has become 1 point. This is
Yes.
one circular part, and so is this.
Ah.
Okay. So what I did was some nice deformation, right? This was some nice
Yes.
deformation.
Yes.
So in that way, if I do this in the reverse, this is called a figure 8. Okay. This is just
Okay.
2 circles. This is 2 circles. Okay. If I just
Yes.
shrunk it down to 2 circles,
Yes.
it's not figure 8 by the, sorry. So 2 circles by the reverse continuous map, reverse stretching, I can make it 1 circle. So you
Okay.
can say that, oh, the 2 circles are same as 1 circles. I work on a continuous maps because I know that stretchings are continuous. And what's the point of knot theory? I can just stretch one string and everything goes shrinks as you tie the knot in real life, and that goes to a point. Every knot is S1, right? Every knot is a circle.
Yes.
That's the point. I said that yes, every knot is a circle in 3 dimensions. That's the definition. But
Okay.
when we are asking that, when 2 knots are the same, I am asking that don't destroy the knot. Don't tie and destroy. You can do mild things. You don't shrink a part to a 1 point. That is a singular point. It becomes a problem. And how do you formulate mathematically? So is it clear
I
that
had a
this,
question that,
yeah,
like in this slide, I can see that like there is R3 and R2. Can I not, can like this thing be n-dimensional also?
n-dimensional? So has Trishan Mondal given the talk? Okay, leave it. So see, there will be a talk. What's the difference between 3 dimensions and higher dimensions? So I should not give a spoiler. Wait for the talk. So for me, it's just 2 and 3, nothing more. Okay.
Okay.
Okay, just wait for the talk, attend it. And now I'm saying, so how do you say nice maps? Nice maps is, there are 2 ways when you want to do mathematically. I can say smooth maps. And in knot theory, exactly the word you need to think is, not for now. So you usually do piecewise linear. So it's, this is the kind of maps you will be looking at later on when you try to formulate knots. And sometimes they represent knots by triangles and it's okay. We'll not go into that. Now, this R3, it's more or less okay, right? This description. How do you say this? The same, you twist it and turn it, but not in a bad way, in a nice way, without destroying it. Now, in maths, you can't work in R3. When you're working in pen and paper, you have your imagination is limited by your machinery. And to do R3, every time you need to open a 3D calculator. So those things weren't there in the times when mathematicians, big ones, they created the theory. So what you do, you project into R2. So what you are seeing right now is a projection onto your laptop screen. That's the R2. So now you can see there are 2 types of movements you can see. So this is a knot. I can wiggle it around in 3 dimensions. These are some lot of different descriptions of the same knot. Now, this is one knot. You are looking at it from one direction of the screen. You can see there is no crossing, right? Now, suppose the screen was turned in a different way and you look at it from this angle, you find there is a crossing. The knot diagram is not changed. Your perspective is changing because of the projection changes. So you have a diagram with a crossing and you have another diagram without a crossing. And I know that these are the same because we just constructed it for you. So how do you formulate it mathematically? These are the 2 big questions. And another type of movement you have. So you have something in R2. This is a knot. Over here. So over here I can have this guy. So you can shift this region to here, wiggling in R2 on the plane. That's also allowed. So all these machine information, lot of information. So these were captured very nicely by some guy in this Mister, and also Alexander proved something like this independently, but it's called Mister's theorem. So I think you can see these moves, this twist. Twist means when you have this is the same as, you can change it by something like this in the figure. This is called the unpoke, and you can change it to this in your diagram. This is the same thing as you can see. And slide, I think you can see the slide. It's a bit not so easy to draw for me. So this is the same thing as what you have here, this guy. So
I had a
these
question,
are
like,
okay.
after looking at this slides, like the knots and everything, the threads, and they kind of like, they are also looking like graphs. Like, they may not be graphs, like, but they kind of look like graphs in
Yeah,
certain
it's
ways.
not exactly graphs, not exactly graph. So
No, not a graph. Like,
how did
obviously, like, they are
yeah,
knots, like
fine.
threads and all that.
So what is our model for knots? So I wrote S1. S1 is the circle in 2 dimensions, right? That's fine.
Yes, yes.
So okay, so just be on the unmuted thing so that I can understand that you've understood. So what do I do when I do a knot? I give a continuous map whose domain is the 2-dimensional circle and which maps to something in 3 dimensions. Okay.
Yes, yes.
Now what are the properties of this map? Can I say that this is a smooth map, very nice map? As it turns out, you don't need it to be very nice. You can have piecewise linear or piecewise continuous. Piecewise linear is this. This is a knot map. Is a very bad looking knot. That's not exactly what I mean by piecewise linear. Piecewise linear means that, so this is something advanced. So 2 points here. So it maps to something smooth. It's piecewise smooth, you can say. That's the best thing you can say here. And you say the word graph. What I have is a simplicial structure. So that should not concern us now. That's heavy machinery. So you are in first year of college, right? Or just 12?
I gave
In what
ISI,
year?
like, I passed the 12th this year.
Okay. So good to know. You will be seeing more of this in your undergrad if you pursue math. I don't want to go into machinery right now. I can just talk machinery for 1 hour then. And these two theorems, this Alexander's theorem and the Mister theorem, this completely classify the knot. So this was earlier. So this means that given a knot or a link, you can just write all the crossings in one part and everything else on the strings. This looks very intuitively obvious because, yeah, you have a point inside it. You just draw the shortest line outside and pull that part apart, and everything else you push to the left hand side, right? But it's a bit difficult to formalize. The thing you need for this is, let me just write out the word we will not be talking about. Maybe you've seen this Jordan curve theorem. So this just says that every curve, nice curve, has an interior and an exterior. Either you're inside this or you're outside this. So doesn't matter. It's a big thing, but not in our lecture. So the thing is that this is too much information. Mister's theorem. You give me 2 notes and I will do every possible Mister move to see if they are the same. That's not possible. So we want some invariant. Given 2 notes, it's very difficult to see if they are the same. But is there any way to ask the converse question? Can I say that 2 notes are different? That's what I call an invariant. You lose some of the information given in the knot, but you have something it's a bit easier to compute, and you don't lose too much information. So I can say that number of connected components. From that, I can say that this that this guy, this is not the same as this guy, because the connected, it has two connected components and it has one. Okay, that's one thing, but it's too little information. And this classifying some basic knobs, this I will come back later. And simple respect structures and operations. This also I need to come back later in due time. So you have some nice invariants, these crossing numbers, minimum number of crossings for a diagram, but in general, it's very difficult to prove that this is the minimum. So you have to do hard manual labor, or you have to use some other machinery. So this tricolorability, it was some also another thing which was developed. So using this, so there are some conditions. If at each of these crossings, so you have to use at least two colors, and either all of the same color or all of different colors. So you can see that this trefoil knot, it can be three colored, and this is a figure of 8 knot. This is 8, figure of 8, this guy. So this is not three colorable. You just look at the crossings one by one. Here is you need three colors. So just do three colors. So all are symmetric and at least two colors are used. So you start with something that has three colors. Okay, you color them. So here you have no choice. And yeah. Okay, so even here this is okay. But if you just follow the crossings one by one, there will be some problem. Okay, so I don't want to follow into this because I have something more interesting. So this guy, Sir Vaughan Jones, so he worked in some stuff von Neumann algebras, which has apparently nothing to do with knot theory. So he has found out one nice relation from that algebra, and that connection and a lot of other work won him the Fields Medal. This was one of the biggest works in the initial years. It was long back, and the polynomial is named after him, the Jones polynomial. So how you define it? So we are not going to define it the way Jones did it, because it was very heavy machinery. So later on, some guy, Alexander Kaufman, he came, and this Kaufman bracket, that was something he defined to very simplify this Jones polynomial into a combinatorial object. But first of all, we give more information to the knot. We give it an orientation. Orientation means that over here I can orient this. Let me give an arrow. It's like water flowing in a tube. Okay. So this is how I orient this. And at each crossing, you have information about which one is above and which one is below. Fine. So what did he do? So we call this kind of crossings as positive and this kind of negative. So you have to look at the picture because I can't say this in words. And so when you have a link diagram, so n minus is the number of negative crossing and n plus is the number of positive crossings. And this is the Kaufman bracket of this diagram. You compute the Kaufman bracket, adjust it by the factor of q power n plus minus 2 n minus and minus 1 power n minus. So these are the factors. This will give you something called the unnormalized Jones polynomial, and to normalize it, you have to just divide this guy by this q plus q inverse. So we call it a polynomial, but it's not technically always a polynomial. It need not be this Kaufman bracket. It can have q inverse terms. This Kaufman bracket, this is defined recursively using three relations, and recursively, I mean, on what? Recursing on what? On the number of crossings.
I had a
So-
question, like what is a normalist polynomial?
It's just a name. Normalized Jones polynomial and unnormalized. So it was history. So some guy defined this polynomial in some way, this Jones guy, and this Alexander guy came, no, Kaufman guy came, Louis Kaufman, and he saw that this is a better way and easier way to compute. And the most natural thing gives you some polynomial that differs by some constant factor. Just that.
Okay.
Okay. And also, just a fun fact, if you want to look at the homology, I'm not sure if we'll get the time to discuss that. Then we can see it's something like reduced and unreduced. There are two versions, both of them are useful. So these are the things. So when you have the empty diagram that you evaluate to 1, so when you have a crossing like this, and the rest of the diagram you don't do anything, the bracket here, this is the way to write. That means the rest of the diagram is invariant. You are changing this crossing. This is, you are smoothing out this first one. Rest of the diagram remains same. Minus q times whatever you get, and the rest of the diagram remains same. And you keep on simplifying the bracket until you get some diagram with no crossings and only circles. And for circles, you remove a circle from the bracket, so you multiply the polynomial by q plus q inverse. Those are all the rules, nothing more. So it's easy to compute, and someone found it that it is actually computation complexity is something a polynomial, I guess. But of course, number of crossings is a point. Yeah. So here you see I've computed something about the Hoff link. You can just have a look. So this is I've oriented the crossings this way. This is the first crossing, and here is the second crossing. Okay, I can draw this. This is the diagram, and both are positive crossings. So here you resolve, and you get the rest of the diagram. This guy you resolve once, so you'll get something like this: q power 4 plus q square plus 1 plus q power minus 2. So you multiply it by q squared because it's q power n plus 2 minus twice of 0, and minus 1 power n minus, so that's 0. You have to multiply it by q squared to get the what we call is our definition of Jones polynomial. So far so good. But you can see that the entire diagram is connected by some local stuff, these crossings. So how do you work with that? So I can say that what if we just look at the local pictures and try to deduce something and compute it that way? So here is something, the state sum model. This is the way that we will slowly move towards Khovanov homology. So at every crossing, you do two things. Either you do this guy or you smoothen it out this way. There are two ways to smoothen it. And one of them just gives you the bracket, and the other one gives you the bracket times minus q. So one of this you call this 0 smoothing, and this you call a 1 smoothing. And so now what I do, I label the crossings 1 to n. So for each of this 1 to n crossings, I can make an n word. So either I make a 0 crossing there or I make a 1 crossing there. So I have a word. And this each element of 0, 1 power n has corresponds to one of our pictures, one of our crossings. So I take a diagram. So this is, so gamma is the smoothing associated to the word A, and I'm just having notation Ka number of ones in A, sum of the number of ones, anyway, and Ra is the number of circles. So this is my exact figure. This is my exact expression. Sorry. So can you read it? I need to see if it's readable.
Yes, yes.
Okay. So this summation is over. Yeah. I'm worried about the dialog box messing up with my notation. Okay, anyway. So here I've attached the computation for the trefoil, but maybe I'll be doing the computation for the Hoff link because that's easier. And this proof is easy. The thing is that looking at it this way, proof you can do by just induction. So, okay, let me do for the Hoff link. Hoff link was something like this. So let me orient it this way, and the other guy orients the other way. So n plus equal to 2, n minus equal to 0. So I have done the smoothings here. So this is 0, 0. Okay, first of all, this is the crossing number 1. This and this is crossing number 2. By the way, Shankar,
হ্যাঁ বলো
yeah, okay. So I think this my Adobe app updated yesterday, and there is some auto type feature. How do I disable it? It wasn't there till yesterday.
I am
Do you know?
not really sure about.
Okay, okay. Anyway,
I have
so
not
that's
used
why
Adobe.
my sure leave it, leave it. That's why the writings are messed up. Anyway,
Okay.
I hope it's read. Okay. So this is 0, 1. So here I'm doing the opposite. So this crossing is merged and this crossing is opened up. So it's 1, 0. And here I have 1, 1, 1, 1. So those are all possible diagrams. Okay. So here for this, I have minus 1 power 0. Minus 1 power 0. Q power 0 because number of ones, and Q plus Q inverse. This squared, this is the number of circles. For these two diagrams, for each of this I have minus 1 times Q, and there is a 1 circle, so Q plus Q inverse. And there are 2 of these diagrams, so I'll multiply it by 2. And here is just Q squared because it's 1, 1. Q squared and minus 1 whole squared times Q plus Q inverse, so squared. So if you add these guys, you will find that you have the same thing. This Kaufman bracket, this is, you add all this. So this is Q power 4 plus Q squared plus 1 plus Q power minus 2. Okay. So how successful was this? This was easily calculated, and using this, there is a computer program which you can write. That's okay. And Jones used it to prove some long-standing conjectures of that guy, Peter Tate. It was something about crossing number, and this will be readable after some time, not exactly for this talk, so I will just gloss over. So there are a lot of open questions. What's the Jones polynomial of the unknot? Unknot means just a very simple diagram. This is the unknot. So given the Jones polynomial of this diagram, can I say that anything having this Jones polynomial is same as this knot? This is an open question. Still, we don't know. Some counterexample has not been found. So anyway, so what is? So there was some development. Khovanov homology. This guy, Mikhail Khovanov, it categorified this Jones polynomial. And now you have every reason to blame me for using this word, because it's not something I should be using this here, and I won't be able to define this without any machinery, so I won't even try. Just see this title which I have made, less drama and more structure. That's the most I can say. So how do natural numbers categorify the finite sets? So given two finite sets, how do you compare them? There's only one structure you have, the number of elements. So I can say that given all finite sets, I divide them into equivalence classes. If the number of elements are the same, I can construct some set theoretic isomorphism that's just associates some element of this set to some other element of that set and perform some bijection. So those two sets are technically the same according to number of elements. So I will say that these are isomorphic, and I will identify all of this together. So all elements of the all sets having the n elements, that will be represented by the number n. So those all will be considered equal. And given two sets which are different means the number of elements are different. So what relation do I have? What structure do I have? So one is less than the other. The number of elements is less than the other. So what have I done? I've seen this, all the sets, all the finite sets. Set of all sets is, there is some Russell paradox, but finite sets, there is no problem. And I'm looking at all of this. I'm reducing them first, which are identical up to some extent, and then I'm saying that what is the relation between them. This is the natural numbers. This is the natural numbers, and we say that this is a sort of categorification. I'm giving more structure and removing some structure as well. So I'm looking at isomorphisms. Isomorphism just means that to same to some extent, and then I'm giving them structure. So, okay. Now the next thing is homology theory. So I don't think I have time to discuss this homology theory or whatever. So in topology, when we study spaces, so at first, historically, people developed something about the Betti numbers, an Euler characteristic. So I think you have seen this graph theoretic math. So number of vertices minus number of edges plus number of faces, that's equal to 2, right, for the planar graph. It's 2, right?
Yes.
Yeah. So I was just checking if you have seen that. So what is this 2? Because you can have a planar graph on a plane. It's a property of the space. It's the property of this plane that the number of vertices minus number of faces, I mean, v minus e plus f, that is equal to 2. If I give you some kind of figure, I am saying that construct a graph that can be embedded here, something like this. So what's the number of vertices? 1, 2, 2. And number of edges? 1, 2, 3, 4, 5, 6. And what's the number of faces? Plus 2. I'm taking this part. So what's this? This is minus 2. So it's a property of the space. If this is my space, it won't be the same. And it's a planar graph if we include this, but I'm forcefully saying that no, I'll restrict it to this space. So that's something called the Euler characteristic, and you can upgrade it to any space. The next level upgradation is the number of, so you can, for every dimension, you can associate a number. So here I'm saying the number of faces is associated to dimension 2, but that's not invariant. I can cut through one face and make many more faces. So that's not invariant. So the same diagram. There is some way to make it precise and give an invariant. That's called Betti number. But the thing is that when you define Betti number that way, the number for dimension 2 and the number for dimension 3, 4, 0, 1, there's no relation between them. You don't know how to calculate and what to do. So that's where the homology theory comes in. I cook up a theory. So this invariant number for every dimension, which I have not defined or not told how to make sense. So each of these is related in a very nice way. That's some theory you will be learning in your bachelor's, undergrads, whatever. That's a very nice theory, and it's long known. So this Khovanov, he developed some upgraded version of that, some graded homology theory, and was quantum Euler characteristic. Now, what the hell is quantum Euler characteristic? So this I have defined Euler characteristic. Okay, but what's quantum here? So look here. So this q power something, q plus q inverse power something, and minus 1 power something. You can recognize this minus 1 power something as edges, faces, vertices. It's 1 minus 1, 1 minus 1 alternating, and q is the degree. I'm forcefully adding a factor q. So instead of having one-dimensional numbers, you have numbers here. Along q, you have something plus minus. Along q square, you have something. So you have some two-dimensional box. And you take the sums along the rows and sums along the columns and you sum them up. That's something you get Euler characteristic. I'm not defining it just because it's too complicated to define in 1 hour. But let me talk about what makes it interesting. So this is strictly stronger. So what do I mean by strictly stronger? It means that I can give you two knots who have the same Jones polynomial but who have different Khovanov homologies. So these are very artificial, so there's no point drawing this here. I can't even draw. I have to give a picture. But even though it's stronger, but the more is that what we have gained conceptually. And it's still easy to compute. The same amount of computation you can do for Khovanov and this. And this is a very big win. This unknown. So if the Khovanov cohomology is just C, or if you are doing it over rational numbers, you will get Q whatever. No, don't do it over rational numbers. If it's a knot and you are doing the calculating it over Z and the answer is just Z, then it has to be the unknot. That is a very deep theorem which I don't even understand. So forget about presenting. But it's a very big win for the theory. And this I have written something functorial up to a plus minus sign. Just give it a hole. So what do I have? What do I mean? This means it preserves structure. So what do I mean by structure? So when I have two knots, K1 and K2, so suppose there is some knot here. I am not doing anything, and here is one edge, and here is something. I'm not caring. So this part I want to join. This is K1, this is K2. So I'll join by this guy here, something like this. So this is K1, this is K2, and I'm joining here. So is the Khovanov is the invariant of this and the invariant of this somehow related to the invariant of this plus this? I'm joining here, not exactly plus, but join. So Khovanov homology, it's easy to find out the relation from here to here. You just have to construct a chain complex and do something. Jones polynomial, it's not that easy. I think it works for some classes of graphs, knots, and you have to do some effort. And for the other knot invariants, for suppose crossing number, it's not a word. I have to say minimum crossing number. That's an invariant. If you join two knots, if the minimum crossing number of 1 and the minimum crossing number of 2, when I join them, is the crossing number of the joined knot the sum of the initial crossing numbers of 1 and 2? In general, that's an open question. It has not been solved. But for alternating knots, it has been solved, I guess, using Jones polynomial and some other kind of stuff. Yeah, but in general, it's a very open question and no one has any idea how to approach that. So in this field, you will find a lot of things which look very trivial and which are very difficult. So there are very interesting things which later on you guys can come up with and help us solve. So this field is a very rich field. When you're studying knots, maybe you can end up studying every branch of mathematics. Everything is connected to knots. So stable homotopy, Floer homology, these are just names for now. Just see the names and enjoy. Someday we can talk later. It connects to representation theory, topology, and homotopy theory. And also, I don't think anyone here has seen manifolds, so let me not talk about that. And there are some ghost terms or phantom terms or magic terms in this quantum
What are
homology.
manifolds like n-dimensional something?
Yeah, I mean, a manifold, n-dimensional manifold is a very nice n-dimensional structure where you can make sense of the word dimension. So what does it look like? In an n-dimensional manifold, you go to a point, look very closely around that point, look at an open set. That will be looking like Rn or some open set in Rn. Locally, it looks like Rn. You just patch them up together. For example, you can say that this circle S1, two-dimensional, it locally looks like real line. So let me just make it precise. So this locally here, this open interval, this is looking like the real open one-dimensional thing. So this is the one manifold. So it matters how you patch it up. So this is not patched up, it's not the same as this one. So yeah, so for four-dimensional stuff, it becomes very, very difficult. And people are trying to use this Khovanov homology to try to cook up some invariants, how to identify them and get more information. So this is it. And quantum computing, something is being tried, but it's not exactly something I understand well.
Yeah, I had a
Okay.
question
Okay,
like
okay.
from your department, where do like most people go? Like for research only or for jobs? Like I was just asking, like in general
I
regarding
think
any.
these general questions should be asked after the talk because, right, you can about the talk you can ask anything in between.
No, no, nothing like that. I was just asking.
No. I mean, what do you plan in future and what do people do in future? See, let's stick to the topic. You don't mind, nah? I'm try. I'm not being rude, but let's just focus.
No, no, sir, it's okay.
So this all I said is that connections to quantum computing I won't be able to explain because I don't understand quantum computing. I can talk about knots, but some people do these connections, and there are very rich fields. So it's not fair for me to talk about these things because Khovanov homology, how I get the differentials, because I have not defined differentials, I have not defined chain complex, I have not defined homology. It's not possible. But I'm just saying that we have a theory, we have some structure, and we have some vector spaces. How many of you understand vector spaces? Maybe some of you understand.
So it's in linear algebra.
Yeah. So for each diagram, you associate some vector space over there. For this guy, you have some vector space. So how many? So for each circle, you assign one vector spaces. So for here, this one, this v plus v tensor v. So in
So
one
like
diagram, you
vector space
tensor it.
is a set where like the vectors are different and addition and few operations like that are also defined.
Yeah. That's it. That's it. Basically, that there is a very particular vector space. I will take this guy. And don't ask me why. This is also an algebra. Why I'm taking this is very deep. It has some connections to the structure of knots, but let's not go into that. We are just
So what
taking
is
this
the
vector space.
XL X what you wrote there XL after the
X
slash?
squared, x squared. Sorry for this,
Okay.
but something is happening to my Adobe thing today. It's getting auto typed and auto rounded this my diagrams. Anyway, so here I have v tensor v. So think of it as just v squared. It's just v plus v. So two separate arrows, separate diagrams is plus v, and two circles in one diagram. So that's v cross v. So you have something here, and there are maps between these maps following the think of the diagrams. And when you have some kernel mod image of these maps, it's very difficult to explain what is a homology theory in such a short time. So maybe I'll
So like
gloss over
what is the
this.
relation between V3 and the type of shapes like
So I
V2,
mean,
V3?
this whatever is in the second bracket, you just ignore. This is the grading. So this means that it is q squared. It's q. So here v3 means you are having q cubed, and v2 means you will have just q squared. And how many v's? That many q plus q inverse you are adding.
Okay.
So you
And
have
what
this
is the
number
like
of
relation between those and the circles and the not?
yeah. You see, number of tensors is number of circles. Okay. And this grading, this guy in second brackets, it's this guy. N plus minus 2n minus plus k alpha is the number of ones in this alpha. So from here, you can just algorithmically construct this guy. So what I have here, I told you some quantum Euler characteristics. So quantum dimension at level 0, this is queued in C0. So these things you can compute. Number of circles I have, number of ones I have, n plus n minus I have. So I can construct this guy. And these maps, it's not possible for me to go into these maps now, but I can show you how I get the Jones polynomial. So here is this. For level 0, you have this quantum dimension of v cross v, and this grading is by 2. From 2, I get q squared, and I have two circles, so it's q plus q inverse whole squared. Similarly, you do for this 1 and 2, and here, when you have a direct sum, you just split it. It's just a sum. Q dimension of direct sum of two things is the Q dimension of first one plus Q dimension of second one. So this is what you get here. So 2Q cube and whatever is this. So that's how you get the quantum dimensions at level 0 and 2. And why I've written C0, I don't have time to say that. But that's the notation. And over here, you take this Euler characteristic was the number of vertices minus faces plus edges. So minus 1 power 0, what I get at level 0, plus minus 1 power 1, what I get at level 1, plus I go on till it ends, the dimensions, and it's a finite figure. So here I have dimension 0, 1, and 2. So that's it, and it gives me back the Jones polynomial. Now, what is interesting, I have got the Jones polynomial, but I also have something more. There are maps between these vector spaces. And these maps give us some really nice stuff, very nice, interesting stuff that will give me some homology. So it's not possible for me to talk about homology in such a short time. Maybe it should take another hour to motivate homology. But let me just say that over here you are getting this figure. Can you see this? This is the complete information I'm getting. So this is the dimension here, and this is the grading. So at dimension 0 and grading 0, I have one factor, and dimension, so these Q's are where I get the non-trivial factors. So this is the complete information what I get from Khovanov homology. So how do I say this is more than this Jones polynomial, and why it's more interesting? Why it's more interesting? For that you have to understand homology, but trust me, it has more structure. So this is some chain complex and chain maps you have. It's easier to work with. You can have, say I'm working in dimension 2. I just want to see dimension 2. I don't want 3. I can do that. But in Jones polynomial, you can't. You have to compute the entire polynomial. It's not easy to compute like this exactly. And it has many conceptual values. So this is the same thing maybe. And I've decided to end here. But there are also some things about Khovanov homology, the exact construction, this complex, what is the chain complex, and why we do it. So before I say thank you, I should say something. This homology theory, that is one of the most important things when you study topology, that is used to classify spaces. And this is a very strong concept. Most of the things can't be done by Jones polynomial. And why it's interesting, it gives you more maps. So when you have finite sets, what do you have? You just have sets. When you categorify them into natural numbers, you can have some order relation among them. That's how you get the natural numbers. So here you get an entire theory. So dimension 1 to dimension 2, there are some maps. From grading 1 to grading 2, there are some maps. I have not defined the maps, but these maps are very useful. So more or less, this is the end of the talk. And before I end, I should say that there is a lot of more things to explore. So what happens, instead of knots, you try to see this tangles, this kind of tangles. Okay. The representations of this kind of tangles, this will be some braids. So braids is, so you permute these numbers 1, 2, 2, 3, 3, 4 to n minus 1n, but you keep track what's going above and what's going under. So the how you represent this and how you study this is the same thing as Khovanov homology if you apply this Khovanov homology to this guy. But one question. If you apply Khovanov homology, you can shrink this to endpoints. You have to close it up. You have to close it up. I could have closed it up in some other way. So how many ways to close up? For every way of closing up, I get some Khovanov homology. So what exactly do we have? We have something over here, some information about the top part, and some information about the bottom part, and here is the tangle. this is some representation theory of tangles. So even Khovanov worked in this, and he is doing a lot of interesting stuff in research nowadays. He's still alive. He's the only one mathematician in this. Khovanov, yeah, he's alive, and I think you should listen to some of his talks someday. Some of them are very approachable and very good. So anyway, so this is where I decided to end. I gave you a glimpse of Khovanov homology, but there are a lot of other directions to study knots, and I think it's about time as well. So if you have any questions, you can ask me anything.
Thank you for such a nice talk. Uh, can you recommend us some resources on this knot theory and for further reading?
So, okay, knot theory, exactly what you want to study. So knot theory is a very big subject. So there is one book by Conway, I'm not very sure. This Conway studies them, and there is one book called K-Notes. So let me write it down. Shanko, just remind me if I'm getting overtime, then I will just wrap it up.
Yeah, no, the 5-6 minutes is
Okay.
fine.
Okay. So K-Notes, there is some website. There's some very concise book on knots. And also the person who asked me, what are you studying right now?
I'm just fascinated by this topic you have presented, so I
I
wanted to.
mean, are you an undergrad or just going to the
Yeah,
undergrad?
in the final year of my undergrad, in the third year.
Okay,
So,
okay. So
I'm,
you know topology, right?
I've just in the I just have had an introduction in the basic concept topology, not in the
Okay.
algebraic topology.
Quantity topology. Okay. So algebraic topology for you, for an undergrad in third year, I will say study it using proper topology instead of studying introductory text. So what I would recommend is that learn some bit of homology theory from anywhere. Clara Law is a good book. It's very heavy as well, concise, but it's a good way to learn homology. It's not recommended for young people in this talk. It's only for
Okay.
third year undergrad.
Thank you.
Only for seniors. Learn homology from this. Then read the papers of Khovanov, the categorification of the chromatic polynomial. No, categorification of the Jones polynomial. Just read it. It's a very nice paper. Very readable. Also, there are many versions of the Jones polynomial. I cheated you guys. The version I used was the one which is easiest to derive the Khovanov homology for. Usually, in the other version, it will be in terms of a variable named a, and it has fractional powers of a, I guess root a or a power 1/3 something, I guess root a, and you have to keep track of those. So I just gave in variable q and q inverse. And next, the guy whose name begins with M and who studies in third year. And the next paper you should read. So from here, let me just write it down. Sorry. So from here, what I would suggest is Khovanov, number 1, and number 2, Dror Barnatan. If you want to study not from the Khovanov homology perspective, there are a lot of other perspectives. You can study Floer homology,
Sure.
you can study low dimensional topology, you can study just knots. So for that, this book is always good. There is one book by Murasuga.
Sir, I had a question.
Wait a minute, let me give my final reference, Conway. Also, I will add some more reference in my PDF when I send it. Yeah, now say.
Sir, do people from your department go to jobs?
Yeah, if they want to.
Okay, sir. Thank you.
Don't call me sir.
Hello? Am I audible?
Yeah, Rishabh, right?
Yes. I have a
Sure.
question. Does this knot theory, especially Khovanov homology, has applications in string theory or quantum field theory from physics?
Quantum field theory. I don't know about quantum field theory,
Okay.
but Khovanov homology is a topological quantum field theory. It is a topological
Okay.
quantum field theory. I've not talked about that. But here's the catch: it sounds very much like physics. Topological quantum field theory is more in mathematician stuff, and it's less physics stuff.
Okay, sir. Okay. Thank you.
Okay.
There
May
seems
I
to be a
ask one
question in the chat.
Okay, let me see. And please don't call me sir, okay? And it's better genus to G. Yeah. Genus, this is correct. If a solid sphere has genus 0, then it's an Euler characteristic of 2. Yeah, it's a solid sphere. So who wrote this? Little scientist. So hello, little scientist. Nice name. So you have a solid sphere, it's just the same as a point. Solid sphere means I can squish it down to one point. So a point has the Euler characteristic of 2. And a empty sphere, that means you can't squish it. It's a sphere. You can't do anything with it. So is your question answered? So no response means yes. What else can I do? Anyone else? Any more questions? Feel free.
Can I ask one question, sir?
Yeah,
It,
but don't call me
it's
sir.
uh, so, sir, what can I refer to you as?
Progna. You can see my name.
Okay,
You can see.
I'll just continue the question first of all.
Okay.
Essentially, in the high school level, I am currently in 12th grade, by the way. At the high
Okay.
school
Okay.
level, we usually see Euclidean geometry being given a lot of importance. But when
Okay.
we move on to undergraduate mathematics in general, Euclidean geometry is treated as very irrelevant. So is the reason for that because topology in general solves nearly all the problems of Euclidean geometry with ease. Is that the reason?
No, because there are different topics. So if you want to study geometry, see, Euclidean geometry is a maybe 5,000 years old subject if you take the very beginnings, if we include the very beginnings. So how much stuff can be there to solve? There are still many unsolved problems, but they're very artificial. And you are forcefully constructing some weird circles and planes and saying that this is equal to this or not. So you have to develop, you have to think about it. So there are a lot of directions it gave rise to. So one direction is topology. People thought and developed this subject. And geometry is very interesting. You can study hyperbolic geometry. So after Euclidean, there's affine geometry, projective geometry, hyperbolic geometry. And in hyperbolic geometry, there is very lot of cutting edge research going on right now. I'm not very familiar with it. And also there is some differential geometry, there is some completely other field, but it's connected to the things I told right now.
Yes,
Someone
exactly. Exactly what I was talking about because actually I have a mentor who actually graduated from CMI, and we were talking one day about the why Euclidean geometry as such is not discussed on the higher level, and he also told me that because of the applications of differential geometry and topology in general, every single
Yeah,
thing that needs Euclidean geometry can easily be expressed in a mathematical format that is just much more viable and generalized via
yeah.
topology.
That's the point. That's the point. You have to simplify things. If
Right,
drawing the diagram is so complicated that I don't even understand what I'm doing, then what's the point? My job is to make
right.
life easier.
That makes sense. All right. Thank you.
Okay. So, anyone else?
Uh, Excuse me, I wanted to ask something.
Sure.
Uh, what uh, what benefit does what benefit do we get by using homology and homotopy theory instead of topology? Is it means what more is there in that theory than topology? Because what I have gathered,
So,
topology is very general. So
point set topology, right?
point set topology or functional topology, any kind of topology.
Okay. So, okay, your question is that why do we, so homology theory and homotopy theory, these are the two big umbrellas of algebraic topology. So whatever algebraic topology is done, it's under these two umbrellas. So you are saying, why do we study that instead of studying point set topology? My simple answer to this is very similar to what the previous person asked. Point set topology is very hard. I give you one problem. It's very difficult to study. It's very difficult. Properties of spaces. So I can't understand an analysis because analysis is hard. I want to do algebra. I want to do get some ring group, some vector space from out of some topological space, in this case a knot, and see what structure I can give to the algebra. I study algebra and deduce something about the knot. That's the main point. Because it's easier and easier to work with.
So it has more structure than a topological space.
No, it has less structure, and that's why it's easier to work with. So if it's not possible to have every same information from the topological space into some algebraic structure and be useful to calculate, because if it has 100% of the information, it will be exactly the same level of difficulty to work with. So you lose some of the information and make life easier.
Okay, got it. So what are the general prerequisites that we require to study these concepts?
This means what?
Homotopy and homology theory.
So depends on what level are you. From your talk and your logo, it seems you are in undergrad first year. So homotopy and homology theory, these two are two independent topics, but usually in a course, homotopy is taught after homology. There is no reason why it should be that case. You should know the basics of point set topology. Once done, then you pick up any good book on algebraic topology and you can learn the homotopy or the homology theory. They are independent subject, but the tradition is to learn first homology, then homotopy. Because there are some calculations, you should get used to them, chain complexes, modules, and you first get used to homology because it's easier. Yeah.
Okay, thank you.
So I am free for more questions, but Shankho, make sure of the time. So I am fine.
Yeah.
And my
So
talk is
we'll
over.
need to be ending the talk now, actually.
Sure. Yeah, you should tell that. Yeah, I am done. So thank you. It
Alright.
was great meeting you guys.
Yeah, thank you, Prognadipto, for the wonderful talk. Everyone is requested to join tomorrow for the next talk on Look Out for Lookalikes, Counting What Really Counts by Saraswata Sen Sharma at 10:30 a.m.